Hi there, welcome back. In the previous slice of physics we talked about torque, and there is one specific kind of torque that manifests itself all the time, and that's gravitational torque, which is related to the center of mass. So we're going to discuss these two concepts in this video. Let's say there's a copper pipe that's a few feet long, and you're holding it vertically by pinching it at the top. So here's your thumb and your forefinger. You know from picking things up that you can hold it stably like this and it can be in equilibrium. So let's analyze the forces that are being applied on this rod while it's being held in equilibrium. So the only contact forces it has are forces applied by your finger. The thumb applies a force to the right over here. The forefinger applies a force to the left over here. And then I have the long-range force of weight that acts on this copper pipe acting straight down. And let's say this is a very symmetric copper pipe, so all of its weight will be acting at the geometric center of the object. We're going to talk about why that is as we get into discussing the center of mass or center of gravity in a few minutes. So those are my three forces, and given that my fingers are holding this here, they also act as a pivot. So two of my three forces are going through the pivot, and so they have no torque associated with them. And this third force, the weight that's acting over here, in this particular example also happens to go right through the pivot point that's in between my fingers, and so it doesn't create any torque either, which is why this pipe is happy staying in equilibrium like this. And now, if your friend comes and pulls this pipe a little bit, let's say to the right, while you're still pinching it like you were, now the forces of your fingers still go through the pivot, because that's where the pivot is, provided by your fingers. But the weight that acts straight down, when I extend it back, it no longer goes through the pivot that's in between your fingers. So in this case, I will have a torque that's associated with this. And if you think about which way this force of weight is going to rotate this pipe, it's going to rotate it in a clockwise manner. So the torque associated with this force is going to be rotating the pipe like this, which will bring the pipe back to its equilibrium position of being vertically down. And this torque, because it's a clockwise torque, is going to be negative. The source of this torque is the weight of the object. And the weight of an object is because of gravitational acceleration or the gravitational force. So this torque is called gravitational torque. Any torque that's associated with the weight of an object is called gravitational torque. Continuing with our pipe example, let's say rather than holding it in your fingers, you stand it on the ground. And if the ground is horizontal, this pipe is going to be happy standing there like that. And that's because the forces acting on it now are a normal force and the weight, and those two will be equal to each other in magnitude, so this pipe is not going to be accelerating into the ground or flying off of it. And more importantly, the pivot that's provided here by the contact with the ground, both of these forces go through there, so the torque in this case is zero, like it was over here where you were holding the pipe vertically down below your fingers. And now let's say your friend comes back and tilts this pipe a little bit to the left and lets go. So now the forces acting on it are the normal force from the ground at the point of contact and the weight that it's acting straight down at its geometric center since it's a uniform pipe. And the pivot point now provided by the ground is over here. The normal force goes through it, so the torque from the normal force is zero, but the weight does not go through the pivot point. It is separated by a distance, so there is a torque associated by the weight in this case, which would act in this direction, which is counterclockwise. So in this case, I'm going to have a gravitational torque that is positive. And as this torque works on this pipe, it's not going to bring it back towards the stable position it was at. It's going to take it farther and farther away from it, so it's going to fall down onto the ground and only come to rest when it's horizontal. So the difference between these two equilibrium, when the torque was zero over here and over here, these two were in equilibrium, but this is considered a stable equilibrium because any disturbance from it brings it back to the equilibrium and it's happy getting back to where it was. And this, even though it's in equilibrium, is called an unstable equilibrium because any disturbance will take it away from that equilibrium state and it will not be able to regain its position on its own. Continuing our example with this pipe, let's say that once it's fallen over and lying flat on the ground like this, you want to pick it up. And let's say you apply a vertically upward force on the left end to pick it up. That looks like this. And the weight acts over here. And the pivot point that's provided by your fingers is at this left end. The weight is clearly not going through the pivot point, so there's going to be a torque associated with this weight in this case. So there's going to be a gravitational torque like that, which would be a negative torque because it's clockwise. Now if you want to pick up this pipe off the ground and not have it rotate and have it be level, you can do it. But there's one special point where you must pinch it. You must grab it right at its center and apply your force there. If you do that, the weight now passes through the pivot point, so the net torque in this case is 0, and so there would be no rotation. Now this point at which you can balance this pipe perfectly horizontally is what is called its center of mass or center of gravity. So these circles in all these figures identify the center of mass, and for this copper pipe that was uniformly distributed, its center of mass was always at its physical center. That doesn't always have to be the case. So for example, if I have this copper pipe and let's say I attach a heavy nut to one end. So here's my nut. So now if you want to pick it up from the center, you would apply a force over here. But now the weight no longer acts at its geometric center. It would act closer to where most of the mass is. So the weight would be acting down like this, and so this would rotate in a counterclockwise manner, giving it a positive gravitational torque. So now to pick it up, you will have to pinch it where its weight acts, which is what's called its center of mass. So the center of mass is at the geometric center of an object that has the same density everywhere, but if it's got an uneven distribution of masses, then it'll be closer to where the more massive part of the object is. And an object would be stable when its center of mass lies directly below the pivot, and that would be a stable equilibrium, or when its center of mass lies directly above its pivot, and that would be the unstable equilibrium. Let's now say that we want to determine the center of mass or center of gravity of this copper pipe with the nut. The best way to do this is to take an idealized case that's equivalent to what we see here. So I'm going to tie all of this with a massless light rod. I'm going to put the mass of the copper pipe, all of it at its geometric center over here, and let's call that M1. And I'm going to put the mass of the nut, all of it concentrated at its geometric center because it also independently is uniformly distributed, and let's call that M2. And we can set up a coordinate system over here. Let's say x is 0 over here, x is x2 for this mass M2, and x1 for this mass M1. The x coordinate of the center of mass will simply be the sum of the products of the masses and their coordinates, so M1 x1 plus M2 x2, divided by the total mass, which in this case would be M1 plus M2. And if this object had a y shape as well, the y coordinate of the center of mass you would find out the same way using just y's instead of x's. So to take an example, let's say this rod was 6 feet long, and let's say this M1 was 1 kilogram and M2 was 0.5 kilogram. And let me just say that the center of this rod, based on our coordinate system, happens to be 5 feet from the origin. So now my x1 is 5 feet. My x2, see, if the whole rod is 6 feet, half of it is 3 feet. So if I'm at 5 feet over here and I come back 3 feet, this would be 2 feet. So now my center of mass would be 1 kilogram times 5 feet plus 0.5 kilograms times 2 feet divided by 1 plus 0.5, the M1 plus M2 in kilogram. So the numerators are kilogram times feet, the denominator is kilogram, the kilograms will cancel, my answer would be in feet when I'm done. So this is 5 plus 1, 6, divided by 1 plus 0.5 is 1.5, and that gives me an answer of 4 feet. And it's 4 feet from our origin, and given that the left end of this rod is 2 feet from the origin, that puts me 2 more feet into the rod. So the center of mass would be over there. And so if I supported this rod with a single pivot right there, it would be perfectly balanced because that's where the weight acts. So it's 2 feet from the left end of the rod, or you can say it's 1 foot from the center of the rod to the left. Now, in case you're wondering if there was anything special about our coordinate choice, we chose this so that the center of the rod was 5 feet from the origin. What if I had chosen the origin at the center of the rod, or the left end of the rod, or the right end of the rod for that matter? Well, in all those cases, you would get a different answer for the x center of mass coordinates over here because the origins have shifted. But when you interpret that answer based on the geometry of the rod, you will always get the answer that the center of gravity, or center of mass, is 2 feet to the right of the left end, or 1 foot to the left of the center of the rod. Those answers will not change. And you can do that for practice and verify that for yourself. And by the way, the general equation for the center of mass would be how many ever parts you have. We only had 2 parts to consider, so we only had 1 and 2 as the subscripts, but you could have more, and you would just add them all up and do the same process. This slice of physics covered gravitational torque and center of mass. We saw that gravitational torque is the torque of an object from its weight around the pivot point, and it's 0 if the center of mass is directly above or below the pivot point. The center of mass, also called the center of gravity, is the point around which the gravitational torque is 0, and for objects with uniformly distributed masses, it is at the geometric center, and we also talked about how to find it for objects that don't have a uniformly distributed mass. Thanks, and I'll see you later.